Hello, everyone. Today, we're honored to have Professor Westermann to give us a talk about in-situ visualization. Ruediger Westermann is a professor for computer science at the Technische University of Munich. Since 2003, he is chair of the Computer Graphics and Visualization Group. Before that, he was an associate professor for scientific visualization in the Department of Computer Science at the RWTH. In 2012, he was honored a ERC advanced grant worth 2.3 million euros for research in the area of uncertainty visualization. Since 2015, he's a part of a Trans-regional Collaborative Research Center, WAVES2Weather, where he supports meteorologists with visual analytics and deep learning approaches for identifying the limits of weather predictability. His recent research activities include stress-guided topology optimization, as well as GPU and machine learning-based methods for data visualization and reconstructions, compression and feature analysis. Professor Westermann, now please start your talk. Thanks.
Thank you. Yeah, then I think I can start. So first of all, thanks a lot for the nice introduction, and thanks a lot for the invitation to present some of our work on neural network-based upscaling and sampling for in-situ visualization here. And also thanks a lot for all the people having interest in this talk and joining us today. Yeah, my name is Ruediger Westermann, and I was introduced already. And let me also name some of my PhD students, especially Sebastian Weiss, Kevin Höhler, and Fatime Farukmanesh. So they have done most of the work I'm going to present today, and without them, these things would have not happened. So yeah, let me just talk a little bit or talk briefly about where I come from. Oh, by the way, if you wonder about the red carpet in the back of me, actually I'm in Copenhagen in a hotel, so that's not my flat, it's a hotel room. Sorry about that, but okay, it is as it is. So yeah, let me now come back to the talk, to the research. Yeah, so I'm grounded in scientific data visualization, and this means that most of the day I'm thinking about the development of efficient and effective techniques to visually analyze so-called space-time fields. Space-time fields are quantities that are structured in space and which evolve over time. For instance, simulated via numerical simulation technology. These quantities typically have a physical and geometric correspondence, which is in particular different to the data we typically see in information visualization, where this physical and geometric correspondence is often not given. And the data usually comes on a space discretization, a so-called grid. Just a discretization which is done in order to numerically simulate these physical quantities, or just a grid that comes from a scanning device in remote sensing applications. It can also be just a scattered point set, depending on how the data has been generated. And here in the bottom, you see a couple of applications. In the top left, we have features in a turbulence field. Then we have a view of the dark matter distribution in the universe. We have a medical data set, and then we have data from a remote sensing device. Now, these are the typical data sets we are confronted with in scientific data visualization. So data visualization is a data science. Let me just emphasize this. And therefore, it shares a lot of similarities with other data science. And of course, it also uses techniques from data science. At the core of visual data analysis, always, first of all, is the question of what is the information that is carried in the data. In order to extract this information, we use existing techniques from data science, or we develop new ones, or we extend existing ones, always with the goal to extract the important structures and then to convey them visually to the user. And of course, we are facing the same problem in data visualization as in other data science disciplines as well. We have to cope with ever-growing data sets. And in particular, we have to cope with ever-growing simulation data sets. The compute capabilities on current parallel computing systems become larger and larger. They become more efficient. And that means that the data sizes just continuously increase. And just as an example, what we see here on the bottom right, on the top, the bottom right, sorry, this is a simulation from such a supercomputer. It's a Westermann convection simulation, and it has a resolution of 9,500 by 9,500 times 600 data points, or volumetric elements. And this means that doing something with this data means that we need to store terabytes of data, and then in order to visualize these data sets, we need to evaluate many billions of samples, in particular interpolations, if we talk about volume visualization per view. And this means that we need to think about scalability of whatever data visualization technique we develop. We have another constraint that is not so present in many other data science disciplines. Well, visualization in particular is used if you want to explore a data set. If you do not know beforehand what the relevant structures in that data set are. And in order to explore that data set, you need some kind of interactivity. It often doesn't help a lot if you can press a button and then it takes an hour and an image is generated, because that image typically doesn't immediately show what you're looking for, meaning that you have to repeat the data visualization process again and again with slightly different parameters in order to finally hopefully see what you're looking for. And this means that visualization very often has to be performed under rather strict time constraints to adhere to that interactivity constraint. And this makes working with these big data sets even more difficult. So scientific visualization is typically performed post hoc, or we call that post hoc. What we mean by this is that we have the data sitting somewhere in on a permanent storage device, on an external disk device, and then we extract features, whatever a feature is, and we render that feature, or we render the data set, the volumetric block, for instance, directly. And in all these so-called post hoc visualization approaches, we need access to the entire data. And this now brings us into a problem. This problem has to do with a divergence between compute and I/O. By compute, we mean the computing capabilities of recent parallel computing architectures. By I/O, we mean the bandwidth capabilities which we need in order to stream the data sets out from the computing device and store them somewhere on a permanent storage device. And as an example, here there is work which has analyzed this in far more detail. And they came up with the result that during the 2010s, the ability to compute increased on supercomputers to orders of magnitude compared to only 1 order of magnitude for I/O performance. Now, this means that we can compute higher and higher resolution simulation grids, or on higher resolution simulation grids, but we lack the capability to stream out the computed simulation results at sufficient rates. That is a process, the problem we are confronted with more and more when using with these high resolution data sets. So it takes longer to store the data than to compute it. And of course, these I/O requirements, they further increase when working with multivariate and ensemble data. Multivariate data means that we not only simulate one single physical quantity like a temperature field, but in meteorology, we have a whole bunch of different parameters like temperature, like precipitation, like pressure, and whatsoever. And this means that it just multiplies the amount of memory we need to cope with. And we also have ensemble data. Ensemble data means that we are not running a simulation just once, but we're running it many times with slightly changed initial conditions or even physical models in order to get, so to say, a spread in the final simulation output, and in order to faithfully capture all possible outcomes that could be envisioned. So, and as an alternative to that classical post-hoc visualization, people have started to think about in-situ visualization. And there's a lot of publications regarding in-situ visualization. Let me just mention one of them here. And what in-situ visualization means that we aim to monitor the running simulation by visualizing in real time on the compute architecture. Meaning that we give up that we can stream out the simulation result from the parallel computing architecture to some external storage device, but we immediately, or let's say instantly, upon the data is simulated on the parallel compute server, we visualize it in real time on that architecture and then stream out images. And these images are then streamed out to the remote client, and then they can be watched there. And of course, this sounds very simple, but in fact, it's fairly complicated because it requires to intertwine the compute and the visualization programs in a way so that they do not interfere each other. And yeah, it requires for the visualization program to then access the data as it currently resides on the parallel computing architecture and under time constraints. And in particular, the first problem, that the data is in some way laid out on that parallel computing architecture, that might become a problem as well. Because you know that if you think about parallelizing numerical simulation codes, you need to think about how to efficiently use the memory resources with respect to the particular memory structure that is given on that parallel machine. And then if the simulation has been done, the data is sitting somewhere on the nodes of this parallel computing machine, then the visualization program needs to access it in an efficient way, reconstruct images, and then use these images to monitor the simulation. So, and the question we have asked, and we have started with this about 3 years ago, is can learning-based approaches, meaning approaches that use neural networks, can these approaches help reducing the number of data samples required by the visualization program? And in the following, I will show you a little bit about of the results we came up with about 2 to 3 years ago. So the idea is to say, okay, well, if we would be able to visualize the current simulation result at a very low resolution, and we could then stream out that low resolution image to the visualization client, at least we would gain some bandwidth, because we don't have to transmit high resolution images. Instead, we transfer low resolution images, and then we can let these low resolution images be upscaled on the visualization client to the full resolution. And that is exactly what you see here. There's an image with a resolution of 320 by 240. This is an image of an isosurface in a numerical simulation data set. Now you see it's generated at very low resolution. If you would just look at the left-hand side image, you could not really say what you see. And then this image is transmitted from the parallel compute architecture to the visualization client. And on the visualization client, a learning-based approach takes takes the low resolution image and upscales it to full resolution of 1280 times 960. And now all of a sudden structures become apparent and you get a far better insight into that isosurface. So what we have used here, or what we see here, is essentially an artificial neural network that is used for upscaling, that is trained for upscaling. It's trained on low and high resolution images of isocontours. So we render a low resolution image, downscaled by a factor of 4, and then we train a network so that the network reconstructs so that the difference to the high resolution ground truth becomes minimal. So meaning that we infer these high-res structures from the low resolution inputs. And the nice thing about this is that because we only require 1/16 of the data samples, of the pixels, we only need to sample at 1/16 of the samples we would need to generate the ground truth image. So meaning that we save twice. Once we save when visualizing the data set, for instance, by shooting rays into the data and then looking for intersections between the rays and isosurfaces. We only need 1/16 of the rays, meaning 1/16 of the data samples to take. And then once we have that low resolution image, we save again because we do not have to stream the high resolution image to the visualization client, but only the low resolution image, so we save bandwidth requirements. So a little bit more detail about this work. So it essentially builds on single image super resolution techniques, video super resolution techniques, and also deep shading techniques, which have been developed in the image processing and computer vision community, where people have looked into that task of, can I let a network infer for something that only gives a coarse representation of something? Can I let a network learn to convert this into the corresponding high resolution representation? And there's in particular work on video super resolution where people have done this and have shown really interesting results. And so we took over some of these ideas and then modified the networks and the training processes with respect to our particular constraints. Just a little bit about what we have done here. So a little bit about the training procedure and the data sets. What we use here is just a residual network, which essentially means that this network learns the residual between a simply bilinearly upscaled version of the coarse resolution input image and the ground truth. We also have trained the network to achieve temporal consistency. We essentially do this by not only considering the current frame, but also the previous frame, and training the network so that it can achieve a current inference result that is temporally consistent with the last frames. We're using the optical flow here and the Navier-Stokes-based regularization or in-painting process. And what is it we train on? Well, we use multiple low-resolution input channels. In particular, for each pixel, we compute at which depth along that pixel the isosurface is hit. We also retrieve the normal vector at that point on the isosurface. And we also consider a mask, which simply says whether an isosurface is hit or not. And then we train using standard L1 losses and the L2 loss to obtain temporal consistency against high resolution channels. And the interesting thing is that in this high resolution channels, we also train against ground truth ambient occlusion values. Now, ambient occlusion is simply that we assume a spherical light source, an environment light source, and ambient occlusion just tells us for every point on the surface how much of that light is actually being blocked by other structures of the surface. And so we give this in the training process so that at the very end, the network can not only infer in the high resolution version the location of the isosurface points, and the normals of the isosurface points, but also the ambient occlusion. And this is nice because ambient occlusion, at least if you do it via ray tracing, that you pick a point on the surface and then you trace rays into the entire hemisphere and look how many rays are actually being blocked by the other structures. That can be time consuming, and letting a network learn this is of course something that can significantly, as we will see, reduce the visualization time. Then we trained the network, and the interesting thing is here we only trained on one single data set. This is the so-called ejecta data set. This is what you see here at the bottom. This is a supernova explosion. It's a time-resolved data set, and this is really the only data set we used in the training phase of the network. So how does this look? Let us first look at some performance numbers, because this already tells a little bit about the principal capabilities of the networks. And what we see here is for the data sets we see on the left, we see the performance we can achieve. First of all, we see here, that is the performance we would achieve if we just render the full resolution volume at the full screen resolution with a standard GPU-based raycasting approach. And then you see here to the left, you see the time it requires to render the low resolution version. Of course, that is far lower because we only render on 1/16 of the pixels. And then you see here the additional time that is required by the network in order to infer now from the coarse resolution to the high resolution. And well, you see that only for higher resolution data sets, the network is a little bit faster, or network together with a low resolution rendering is a little bit faster than the high resolution rendering. So it requires about 100 milliseconds for low resolution rendering and network inference, and 160 milliseconds for the high resolution rendering. Of course, this becomes better, or it looks better for the network-based approach if we also compute high resolution ambient occlusion. If we would compute this manually by shooting rays into the scene, this requires far more time, and the network can just infer this in addition to the normal and depth values without any extra cost. However, if you look at these timings, and I would like to explicitly emphasize this, we could say, oh, we can smile here, because the network is faster than the high resolution rendering. That is true. On the other hand, it is clear that what we see in the result, or when looking at the result that is inferred by the network, that is not the accurate image of the isosurface. It's just a nonlinear regression, let me say, of the low resolution image that is then scaled up to the high resolution, meaning that we introduce errors here into the process. And this is something we have to keep in mind. And I will come back to this problem of the introduced errors when doing neural network-based inference later again. We have then performed a couple of tests where we in particular compare the reconstruction quality that can be achieved by the network with the quality that can be achieved by simple bilinear and bicubic upscaling. And all these tests, including the PSNR, the peak signal to noise ratio, and also the structural similarity index, which is a statistical measure using means and variances of certain sub-windows in the image, they all consistently show that the network-based approach is better than bilinear and bicubic network. At least some success here. And the curves show this. For instance, you see these curves here where we have the error. Here we can assume that the maximum error is just 1.0, meaning that if I allow that error of 1.0, then for all the methods, of course, 100% of the pixels are within that error bound, that maximum error bound. And then if I decrease that maximum allowed error, then I see that the blue curve, which depicts the network behavior, is consistently above the other curves, meaning that more pixels stay within that error bound. Now that is nice. On the other side, on the other hand, we have to say, no, the maximum error bound cannot be ensured. No, that is a big problem of these networks. I cannot say I don't want to be above 0.1 in the error per pixel. That is impossible. No? And this somehow also limits the applications of this kind of deep learning based approach in certain applications. Yeah, some more visual results here to see how the inferred images then look like. For instance, here now we have another simulation data set. This is a Richtmeier-Meshkov simulation. It's a data set the network has not seen in the training and validation process. On the far left, you see the low resolution image that is generated. Then in B, the second image from the left, you see the bilinearly upscaled version that you would achieve if you do a bilinear upscaling on the low resolution image. And then in the third image, you see the result of the super resolution network. And on the right, in the right image, you see the ground truths, the full resolution rendering. And what you see is that, we now see far better the spatial structures in that data set. We see the overall shape of the isosurface surface, including fine-grained features very well. Of course, the visualization is not as sharp as the full resolution result. But that is clear, because I mean, the network does not have all the information we see on the right-hand side, but somehow from the coarse representation needs to infer on these high-resolution structures. But nevertheless, I think we clearly see, in particular, the advantage over just bilinear upscaling, and for bicubic upscaling, it would be essentially very similar. We also can look at a completely different data set. Now, for the data set before, we could have said, okay, yeah, this is also a simulation data set, and probably the geometric structure of the isosurface has certain similarities with the structures that the network has learned. Now we see a completely different data set, which has then been processed by the same network. Here in the bottom left, you see the low resolution image that has been created and then given as input to the network. And then in the middle, you see the result of the upscaling network. And on the far right, you see the ground truth. And I think we can say that in many areas, the network is really good in reproducing the ground truth renderings, but we also see that in some other areas the network has problems. And this is essentially that whenever a structure is not seen in the low resolution image, and in particular in this case here, where the network then sees a data set, or sees a rendering of a data set, which has never seen before, then the network cannot simply hallucinate the structure which is missing here. In other parts, where the structure is already, at least to a certain extent, to a certain degree of detail, visible in the image, the network can do a fairly good job. And we see in particular that the ambient occlusion, which is also shown here, fairly well matches the distribution of the occlusion values in the ground truth image. So we see here also a comparison between the result of the upscaling network on the left-hand side, and on the right-hand side, we have a full resolution rendering of the same volume, but the volume has first of all been low pass filtered in order to reduce it to a smaller resolution. Because many times people ask, okay, if you do what we have proposed by looking at the coarse resolution screen or coarse resolution image, could you not just use a coarse resolution volume and then do the very same? So we see here that in that low resolution volume, many fine detailed structures have already disappeared. And there's no hope that a network can reconstruct them faithfully. That's the reason why we did not follow this approach any further. So there's another thing we can do here, and that is also interesting. We can, of course, do the resolution, or we can select the resolution at which we want to render the volume adaptively. For instance, that we have done here. So you see in this image here, now we see that within the red circle, we have sampled the volume at full resolution. In the green shell, we have sampled with a resolution decimated by a factor of 2 in each dimension. And then in the outer region, we have sampled with a resolution that was decimated by a factor of 4 in each dimension. Meaning that overall, we need 11% of the samples, and then we obtain the result if we let the network reconstruct, from these samples, which we see here on the right-hand side. And this is interesting because it essentially allows you to do things like what we call foveated rendering, where we only render at full resolution where the user has focus. Now we could do that by eye tracking, for instance. And in the surrounding region, where the user doesn't have focus on, we can use a far lower resolution, and in this way significantly reduce the number of samples to take, the number of pixels to reconstruct, and therefore then also significantly increase the frame times. So questions, or first questions and insights. Well, we have seen that we need to sacrifice quality for I/O bandwidth. If we want to use less samples and want to stream less pixels, then at least if we use networks, we need to sacrifice quality. And that can be acceptable if we just need let's say, a rough monitoring of a currently running simulation. But we also need to be aware of the fact that we may miss features here. So meaning that if we want to have an accurate visualization of the structures, then we need to be careful. We have also seen that the network evaluation costs time, and we need to embed the network into the visualization program if we want to use it in situ. And especially this is something which, in my opinion, is very often a little bit forgotten in papers in visualization. Networks are slow, I would say. Visualization algorithms, they have been developed over the last 20 years, and many of them are very sophisticated and produce images at very high speed. And this means that if a network is not fast enough, it can easily happen that even though the result of the network is good with respect to quality, it needs to spend far more time than a visualization program would need in order to re-render the data multiple times. And that is something we need to consider. And this is something, by the way, I will also consider in the next part of the presentation. There's another question here about how to train networks. I have shown examples where we have trained the network on a simulation data set, and then we have used it to infer high-resolution images from images of other simulation data sets, and, for instance, also for images of medical data sets. And we have never done this, but I think if you would retrain the network for data sets coming from medical scanning devices, you would definitely be able to increase the accuracy of the inference process. We have never done this, but I think there is really something we can achieve if we would do so. So taking specific classes of data sets, and then for each of these classes having a pre-trained network that can then be used for other instances of the very same class. Yeah, and another thing, of course, is if I have trained the network, and we have seen this to a certain extent when applying the network that was trained for simulation data, we're now using this network to infer a high-resolution image of a medical data set. There, the network all of a sudden sees structures which it has never seen before in the training process. And that makes it really difficult. And that brings then back what I said before, that we should rather train networks for specific types of data sets. In the following now, I would like to focus in particular on this point here and ask the question, okay, can we improve the accuracy in the reconstruction process by spending samples where needed? And this brings me to work we have published 1 year ago, 1.5 years ago, on adaptive sampling and reconstruction for volume visualization, where we have asked the questions, okay, instead of having a uniformly coarse resolution across the entire image domain, can we not just learn a network to only place or to place samples with a higher density in those regions which are deemed important by the network, and just represent other regions with a lower sampling density, and then reconstruct the image from these adaptive sampling patterns. And this brings me to a quite involved pipeline which we have trained, and this pipeline essentially does the following. It's a pipeline that is trained end-to-end based on the final loss, which is coming here at the very end, the final loss, which is computed as the difference between the inferred network result and the ground truth image. And what happens here is the following. So we start with a very low resolution image. That image now has a resolution that is decimated by a factor of 16 in each dimension. And now we have trained a network that infers an importance mask from that low resolution image. And this importance mask indicates those regions in the image where the sampling resolution should be increased. And in other regions, where you see low brightness here, the network has told us, okay, here you don't need as many samples because the variation in the structures is presumably rather low. Then we sample adaptively with respect to this learned importance or inferred importance mask. And then comes a reconstruction network. And this reconstruction network from the adaptive sampling pattern and the values of the occurrence of the isosurface, which is seen along these adaptively distributed samples, this network then upscales and generates a high resolution output, which is then compared against the ground truth image in order to train the network to the optimal state. So, and this is now nice because it really allows you to do a very coarse resolution first rendering. And by the way, I need to correct myself. It was not a factor of 16, but just a factor of 8 we used here in the low resolution or for generating the low resolution image. And what you of these adaptive color samples to the full resolution image, and this is what we actually see here in this result. Okay, so this works fairly good. Now we can look at some more examples and in particular focus on certain structures. So we see here on the right-hand side the ground truth. Now this is again the Richtmeier-Meshkov simulation we have seen before. And on the left-hand side then we have adaptively sampled with only 5% of the samples or of the pixels, and then used the network in order to do the reconstruction. Then you see that some features, well, I would not even say features, I would say the differences are mostly in the, so to say, in the overall look, it seems that the brightness is a little washed out here. No, the illumination is a little washed out on the left-hand side. But if you look at the features, if you look in particular at the silhouettes and the boundary of the features, we have the feeling that the reconstruction is fairly good. Of course, we are losing a little bit of structure here. No, that is, of course, not what we see here. But if we consider that we only used 5% of the samples, then I think this result is already fairly good. We can go further now. Look at a different example. No, this is a jet simulation, also a numerical simulation, computational fluid dynamics simulation. We see on the top right, we see the adaptive sampling mask, where the density of the samples is indicated, and then again we see the results when using these adaptively located 5% of the samples and the reconstruction and the ground truth on the bottom right. And here in this example, you see that we really get a very good reconstruction of even very fine scaled features, like these interior silhouettes we see in these two close-up views. We can also see this, and I hope you can see the animation over the internet. We can see this in the animation. So where we see here now the adaptively, the sparse samples, the distribution of the samples, and here you see the reconstruction. And in a second, then you see in the left part the ground truth and in the right part the reconstruction. And if you actually, well, it's very difficult to tell the difference. And really keep in mind, on the right-hand side, we have only used 5% of the samples, or we have only sampled the data through 5% of the pixels. And then the network has done the reconstruction, and the quality is really almost indistinguishable from the quality that we see on the left-hand side, where we have rendered at full resolution. We can also do this for direct volume rendering, where we don't have an opaque isosurface, but we now accumulate color and emission along the rays of sight. Here the sparse set of samples, and now the reconstruction. And again, if we then compare to the ground truth rendering, we see that we can hardly see any differences here in the renderings. And now we come to the performance of this approach. And so this table here in the bottom, that tells the story, I would say. What we see here is, and that is indicated by the red color, that if we have rather low resolution volume data and low resolution screen resolutions, the network cannot really be faster than the ground truth rendering. However, what we see, if we look at in particular these numbers here, if you have a very large volume of 2K to the power of 3, and if you render to a 1K by 1K screen, but now we only use 5% of the samples, we achieve a frame rate of, or we achieve a time per frame of 333 milliseconds. And here in this case, now the ground truth rendering would be almost 3 seconds. So this shows that the performance of this approach seems to scale well to higher resolution data sets, because then the full resolution rendering becomes more and more costly. And then every sample, so to say, we can save counts. And at the very end, the network is then really able to considerably outperform with respect to performance the ground truth rendering. However, we still have to say the network can produce errors in the final reconstruction. That is something, of course, which is not in the ground truth images. So I also would like to look at a second alternative to post hoc visualization. What I have talked about so far was the classical in situ approach, where we want to bring the visualization to the compute server and then run visualization there. But of course, we could also think about a slightly different approach. We could say, okay, if we can instantly compress the data and stream out the compressed data in real time, then on the remote visualization client, we could then work with this compressed data stream and visualize it. And there's now a couple of different possibilities how to do that compression in quotation marks. First of all, we could just extract certain features from the data and stream these features. It's also not really a compression, I would say it's a compactification of the data. We just extract relevant structures, which are then, with respect to the memory, they require far more lightweight than the entire data set, and we can then stream these features over the network and visualize them. And this is, by the way, something that has been done for the last couple of years already in situ visualization. We could also just compress the data and stream it, use just classical compression algorithms, and then stream the compressed data out. And then, of course, the problem becomes, what do we do with the compressed data stream? Most of, as I said, most of the ad hoc visualization algorithms, they need access to the entire data set, meaning that we have to decode the full data set. And the question then becomes, do we have to decode the full data set at once? Or can we use random access to the compressed data stream and reconstruct just the data at certain points in space? Now, this would be great, because then I don't have to first transform the compressed version of the data set into the full resolution version, which might let the memory requirement explode again. But I could just adapt my visualization algorithms so that they now use random access to the compressed data stream. Yeah, so I have a couple of approaches now, 3 approaches, where we have investigated the question whether learning-based approaches can help to compress the data and enable random access. I think due to the time limitations I have, I will just skip the first 2, simulation upscaling and variable-to-variable transfer, and I will just jump right away to the last one, where we have thought about whether neural network based approaches can be used to encode the data set in a contact form from which the original can be reconstructed by using random access operations. Now, because the slides are available, you can look into the other 2 approaches as well, but I really think the last one is probably the most interesting one. So this last approach is about learning-based data compression. And as I said, the question here we had in mind is whether networks can transform a field into a compact yet feature-preserving representation, from which then the data set can be decoded so that the visualization program can use it. And the question, of course, which is related to in situ visualization, can this representation be computed in real time during the simulation? I will address this question a little later, or I will tell you whether this is at least currently possible or not. Let me just first of all briefly talk a little bit about compression algorithms, and in particular lossy compression algorithm. I don't talk about lossless data compression algorithms which already exist, of course, but which typically cannot achieve the compression rates we would require when working with these very large data sets on these massively parallel computing architectures. So here we have a representative compression schemes like the T-trash algorithm, which works on tensor decomposition. Then we have here the CUDA compress, which works on a wavelet compressed, on a wavelet decomposition of the data, and then use quantization and Huffman decoding. Here we have the CUDA SZ. They use a different predictor in order to compactify the data, but also do then quantization and Huffman encoding. And here on the right-hand side, we have a fast texture compression approach. And you see, if you look at the compression rates, that they differ strongly in the, let's say, typical compression rates they can achieve, 1 to 1000 with the T-trash, 1 to 20 to 50, let's say, with the ones here in the middle, and then rather low compression rate here for the ASTC. When it comes to speed, then encoding and decoding speed, we see the opposite behavior. It requires seconds to minutes to encode and decode data that has been compressed via tensor decomposition. We are in the millisecond range here for the Q-compressed and the QSZ versions, and we have more or less instant encoding and decoding for the ASTC dataset. And the question, of course, now is, can we compete with these approaches when using neural networks? By the way, yeah, for all these approaches here, blockwise encoding and decoding is possible. Now, this is a nice feature, meaning that if I want to now throw my visualization algorithm on the data set, I do not have to decode everything at once, but I can do this blockwise on demand. Yeah, and now this question of whether learning-based approaches or network-based approaches can help us here guides us towards the so-called scene representation networks. Just in brief, they have been introduced in 2020 by Mildenhall. There was some ongoing work before, also into that same direction. And what they essentially do is they propose networks that can learn a mapping from X, Y, Z, spatial coordinates and directions in polar coordinates to RGB and transparency values. They introduced these networks essentially in order to generate models from images of a model. And they showed that such a mapping can be learned very effectively by neural networks. And then there was work 2021 on the, I think it was the CSIG-VIS conference by Liu, Yang, Levine, and Berger, where they introduced volume scene representation networks. They said, okay, we can learn networks, or we can train networks to learn a mapping from X, Y, Z spatial coordinates to a density value, to a volumetric density value. And they showed really impressive results with respect to compression rates that can be achieved, like even 1 to 2048 in the left-hand case and 1 to 256 on the right-hand side. However, what they also showed was extremely long training and rendering times. For instance, for the volumetric data set we see here on the left-hand side, the training took about 500 minutes. And then, and this is even worse, the rendering takes about 3 minutes. And this is something which is probably not acceptable, right? Even if you have such a high compression rate, if it now takes 3 minutes to render the data set, this is something you rather want to avoid. Now, rendering the uncompressed data set takes about 150 milliseconds. Here on the left-hand, on the right-hand side, we have the very same here. The rendering process is a little different. This is a path-traced rendering, so meaning that the rendering even takes significantly longer. Yeah, but still, with respect to rendering the uncompressed data set, which is just about 5 or 6 seconds, the rendering times are really, I would say, unacceptable. Yeah, but nevertheless, I mean, they really brought that idea of using these scene representation networks into the visualization community and demonstrated that really excellent compression ratio can be achieved. So now what we did, and this is a paper which just got a minor revision, so it's more or less accepted in the computer graphics forum. We have shown that these volume scene representation networks can be made fast. And just in brief, what we have done, well, we have looked at the underlying hardware that is used if you use network-based inference. We have also looked at the internal structural layout within CUDA. We consider the number of threads per so-called compute warp in CUDA. We consider the number of matrix columns in these tensor core units, which are used if you work with networks on recent GPUs. We have looked at how much shared memory you have. And by considering all this, we came up with a very fast realization of these volume scene representation networks, which still has the very same benefits of giving very high compression rates, but is significantly faster. In addition, we introduced a 3D latent grid, which works extremely good in that case. This latent grid is inspired by network-based geometry encoding, where people have looked at, can we encode geometric representations, so geometric models, even hierarchically, in a network. They call these internal latent space representations, and they showed that in these internal latent spaces, or in these internal latent representations, which are learned by a network, the information is maintained, which you need in order to faithfully render the geometry. We took that approach over to the volumetric case and now use a 3D Cartesian latent grid, which is filled with learned n-dimensional latent vectors. This grid, or the values in this grid, are just jointly trained with the network weights and biases, which are required by the volume scene representation network to do the decoding. And then what we have is the network architecture we see on the bottom right. So at each point in space, whenever the ray wants to sample the volume at a certain point, it first reconstructs the value from the latent grid, this latent value. It gives then the x, y, z coordinate of the current sample and that latent vector into the network. Here we employ Fourier features, which essentially increase the spread in these x, y, z coordinates, so that the network can better discriminate these features. And then we just pass them through the network and let the value be reconstructed. And interestingly, if you now look at the results, we see that we can significantly improve the rendering. Here, still for the very high compression ratio, and the training and rendering times of the volume representation networks, we see now that we get, I would say, interactive frame rates of 1.7 seconds and 3 minutes of training. And I think this is now a nice result, because this really allows you to now instantly use these compressed data representations, internally encoded into these latent representations, and you can access them in a very efficient way and build them into a volume raycasting approach, which is then able to very efficiently render these data sets. And also on the right-hand side, we see a similar improvement in the rendering times, even though keep in mind that the rendering times are so low here because we use a path tracer here to render the volume, which not only considers the primary rays, but then also takes secondary, tertiary, and higher order rays into account to simulate global illumination. Yeah, and just a little bit of analysis here. If we look at the results now, which can be achieved, maybe the first result we should look at is the one here. Now what we have here is for the alternatives, T-Trash and also CUDA compress. That was the one similar to the MPEG decoding, but using a wavelet decomposition. And what we see now here is that the fast volume scene representation networks are significantly faster than the other alternatives, but with respect to the compression ratio, they are more or less in the similar range. And this really makes me believe that these network-based compression approaches have great potential to make it into workflows, into simulation environments where high-resolution data sets are generated and where we need to monitor these simulations by then first compressing the data, sending the compressed stream over, and then rendering directly from that compressed latent representation. Yeah, some more results, but I think, no, okay, I have a little bit of time just to show how the compression affects the quality of the final results visually. Now, what we see here is on the left-hand side is a ground truth rendering of this of the data, the volumetric data set, and here on the right-hand side now we see the fast volume representation network at a compression rate of 1 to 1000. Now, I think that's really a very high compression rate, and what you see is, well, I mean, of course, you lose information. No? That's clear, and that is what I said before. No? We cannot hope for an accurate reconstruction, an error-free reconstruction. But if you look at the structures, no, I think we see that most of the structures are very well resolved. If you look at other compression algorithms, like here, for instance, the t-trash, and the time here was 4 seconds. By the way, here the t-trash is now 10 seconds if we render in a blockwise fashion. Then we see, okay, it has different types of artifacts. And I would say that even though the SSIM matrix values doesn't differ so much, I would say that the network does a better job here because it somehow seems to consider spatial coherence in the reconstructed results. No? It gives you a more smoother look. If you look at CUDA compress using the discrete wavelet transform, you see it looks completely different. You have these kind of block artifacts coming from the quantization of the wavelet coefficients. It looks more sharp. I would also say that maybe it's not so that more features are lost. No? It's just that you have this kind of staircase patterns here, which can be somehow, I would say, yeah, inconvenient to look at. No? But I wouldn't really say that features are lost here. But also we have to consider that the compression rate is far lower than the compression rate we could achieve with the t-trash algorithm or the volume scene representation networks. Yeah, and then also the approach by the first volume representation approach, and in particular here, we see that the rendering times are far higher compared to the fast volume scene representation networks. So one last slide here on the scene representation networks. We can also now use these fast volume scene representation networks for time series prediction. And what we do here is very simple. No? You remember I have introduced that latent grid, just a low resolution Cartesian grid in which we have latent vectors which are learned by the network for a current data set, or now here we do this for different keyframes of a time sequence. And during evaluation, what we then do is we only render from that latent grid, meaning that at each point in the 3D domain, we just do a trilinear interpolation in the two next adjacent key points or key volumes, and then we do a final linear interpolation between the reconstructed latent vectors at these two key points. And then we take this interpolated latent vector and throw it into the network, and that the network reconstruct it. And this is nice, and you see the results here. Now on the left-hand side, we see the reference, and on the right-hand side, we now see the network reconstruction, which only takes, this is what we see here at the bottom in that graph, which only takes the key points at every 20th time step, and then interpolates between those. Let me just go backward and show this again. And we see, at least at first glance, there doesn't seem to be a considerable difference in the reconstructions. Even though we only store really and use every 10th data set in the middle example, and then interpolate over time from these latent spaces, as I have explained it before. So let me come to a summary statement. And let me maybe first come to a summary statement which I have left out before, but I think there's a couple of points which I need to at least briefly address. Right. That was first insights and challenges after, or first insights after we had done the upscaling approaches. We had finished the upscaling approaches. And we looked at whether these approaches are ready for practical use. So, and so one of the things is that, yeah, one other thing we thought about, would it be even possible to just in a training step, train on low resolution simulations against high resolution simulation results, so that then at runtime we don't have to perform the high resolution simulation anymore, but we can just do a low resolution simulation and infer the high resolution result. That's some other work we have done. It's also on the slide set, but I didn't talk about this. And the problem here is, of course, that very often we don't have these low and high resolution simulations. They are simply often not available. And one of the questions in metrology now is, can we, for instance, use data augmentation? No? For instance, if someone tells you, okay, I can only, because of time limitations, afford a low resolution simulation, but I have measurements at stations across a certain area. Can I augment my low resolution simulation with these measurements in order to then upscale the simulation result to a higher resolution? You know, that is something I really consider to be interesting. People are thinking about this. I'm not sure whether someone has come up with a good idea how to do that so that the reconstruction is at a certain accuracy. What we have done so far, we have never done so far, we have never considered physical constraint during the inference. Now, this is something, of course, others are actually working on at. You know, physics-inspired networks with physical priors and regularizers. You know, for instance, if we want to have a network that infers from a low-resolution flow field to a high-resolution flow field, then we should, yeah, specify a prior that tells that the inferred flow field has to consider or has to adhere to some physical constraints. People do that, and I think if we would integrate something like this into our upscaling networks, we could further decrease the reconstruction errors. It holds for all these network approaches that it's difficult to predict unseen physical phenomena. Therefore, as I said before, we may have to overfit to certain simulation classes. And then if we have a new data set, then we pick the trained network for this particular class, for the particular class the data set is coming from, and then we use that for inference. Yeah, let me just leave out the last points here and rather go to the final slide, to the final concluding remarks. The summary statement. Yeah, the first results in the field of applying deep learning approaches in visualization, in scientific data visualization, I would say are promising, as I hopefully have shown here in this talk. But these approaches also show conceptual limitations, as we have also seen. Error bounds cannot be guaranteed, and we may lose topology if we let networks upscale from coarser resolution to higher resolutions. And this, of course, can be problematic. We have rather long network training times and evaluation times. And that is also something we have to think about. In particular, if we think about whether networks which compress a data set can be used in situ, well, it means essentially that so far, for every new data set, the network would have to be trained for that data set. And this requires a long time. meaning that also here we have to think about whether we could use pre-trained networks for certain classes, and then maybe just adapt these networks for every new instance of that simulation class. And that brings me to that point here, overfitting instead of generalization. Many of the approaches we see in visualization these days do overfit to certain data sets. And of course, that is something we don't want. We want networks that can generalize, that are trained ones, and can then be applied to many different data sets, which are without having to retrain them. Yeah, lacking explainability. Well, we have looked into a couple of techniques which are typically used when using networks for classification tasks in order to explain the decisions of the networks, or in order to see what kind of structures are most important for the decisions the networks do. And we have, to be honest, merely seen that the networks seem to focus on regions where we have sharp gradients. And yeah, that is somehow intuitive, I would say, because that's where the information is sitting. But it's also kind of disappointing because it doesn't really tell us anything about, for instance, causalities in the data. What are the future challenges with respect to what I have just said? Well, I think we need to think about how to make networks faster. We need to think about specific hardware implementations. We also need to hope for new hardware coming out, and which make network inference faster than today. And then we need to think about things like pre-training, instant training, transfer learning to go towards the generalizability of networks. That is, in my opinion, in scientific visualization, really something we have to address more aggressively. Because as long as we need to pre-train for a certain data set, the practical use of all of these approaches will be rather limited. Another thing is, I'm interested in the question, can we learn from features and topologies? Up to now, we have primarily looked at, can we learn from the data? Can we look at the data and then compact the data and then infer the initial data from that compact representation? Another approach would be to say, well, let's first extract features, or let's first extract the topology, the vector field topology, a scalar field topology, and let's now train networks to infer from features and topology to the data. That would be also something that we need to keep in mind, and I think that could work well. Yeah, and then, as I said, we would like to integrate causality to better compress and reconstruct, meaning that we would wish to have networks which can also learn causalities in the data. We know from work in the field of AI that the networks we currently use do not do that per se, meaning that we have to think about how and whether at all we can achieve this. This is something which I think it's just important for all the communities working with these AI methods, working with neural networks. I'm not sure there's already a solution to this problem, but also in visualization, we would greatly benefit from any approach that could let networks learn causalities in the data. Yeah, and this brings me to the end of my talk. Thank you very much for your attention. And of course, now I'm happy to answer questions.
Okay, let's thanks Professor Westermann for the great talk. There are many questions. A few of them. The first one is that audience have not understand the technical details about the super resolution and need more explanation. His question is that the comparison for in situ visualization, it will reduce the resolution of the 3D data set. However, the rendered image is still high resolution, and the super resolution is used to increase the resolution of images. His question is that how to use the super resolution to improve the rendering result.
Okay, let me just go back to that where we introduced that. So what we do here in that super resolution approach is just the following. Assume we have a data set, a data set with a certain resolution. And you want to render that data set on a high resolution image. Or what it means high resolution image. Let's just say you want to render that data set. I think we see it here. So now we have this medical data set that has a certain resolution. And now what you would typically do is you render that data set as we see it here on the right-hand side. Let's assume you have a 1000 by 1000 pixel raster, and then you shot a ray through each of these 1000 by 1000 pixels. You then step along these rays through the volume, and you determine for each ray the first intersection with the isosurface. And this means, if we talk about computational complexity, what you have to do is you have to do 1000 by 1000 ray traversal operations. And each traversal operation requires you to access the data in that volumetric data set. And now what we do in our upscaling approach is we only render to, let's say, a resolution of 256 by 256. And then for each of these 256 by 256 rays, we compute the intersection with the isosurface. Now that means that we have far less pixels or far less rays we have to consider, meaning the rendering is far faster. And then this low resolution image which we generate, this is then upscaled to the high resolution image which we see here. But this upscaling, this is done on the visualization side, on the client side, meaning that where the data set is sitting, let us assume that data set would be sitting on a parallel computing architecture where the data set has been generated. On that architecture, we only would need to render a very low resolution image, and then this image is streamed over to the visualization client, and on that visualization client, the super resolution network then infers the high resolution image. That's the basic approach. And that means, first of all, we make the generation of the image, of the low resolution image here on the compute server requires far less time because it's generated at a far lower resolution. Then we only need to stream over the network far less pixels. We also save bandwidth requirements. And then the network is used in order to upscale the image on the visualization client. That's the basic approach. So if you could combine this approach with a in-situ, with a numerical simulation program, then in a far more efficient way or in far shorter time, we can generate images and stream them over to a remote client where then the running simulation could be monitored. Yeah.
Okay, thanks. And the second question, usually do we need to train a specific model for a certain data set, or we can train a model for a set of a similar data set?
Right. So in these approaches here, in the upscaling approaches, that is what I have shown here, we have only used one single network that was trained on the ejector dataset. So training and validation of the network was only on images of the ejector dataset. And then this single network is used for all other datasets. So in this case here, so to say, we have a network that generalizes, because in that ejector data set, the variation of the structures is far high, meaning that the network learns, so to say, a lot about the structures in that data set. And then the network can be also applied to other data sets which have never been seen. If you talk about the compression, in the compression approach, the very last approach I talked about, there the fast volume representation network is trained for each new data set anew. Now there we overfit the network to the current data set. And that is exactly the problem I was pointing to at the very end, because this makes the networks rather impractical. Because if for every simulation you need to first train the network for the data sets this network produces, then that probably takes more time than the simulation itself. So therefore, it's so important to think about generalization and to think about how to overcome that overfitting to a certain model.
Thanks. There's the third question. Since there are many challenges, such as the uncertain structures or the details loosened by low-pass filters, how can we evaluate the possible introduced uncertainty or misleading by the networks?
So, as I understand that the question is about the errors that are introduced in the inference.
Yeah,
exactly.
Is the result accurate? Can we trust the result?
Yeah, as I said, no, the problem. Let me go maybe back to the curves here, which we see here. Now, I think we see this quite nicely here. If you look at the blue curve here, then, for instance, if we look at an error of 0.01, so the maximum error in the reconstruction can be 1, let's say, normalized to 1. Now we say, okay, if I have an allowed error of 0.01, I see that about 70% of the pixels will be below that error. But the remaining 30% of the pixels are above that error, and I cannot tell how far above that error they are. And that's one of the problems. The errors cannot be quantized. So I cannot give bounds for the error that are produced by the network. That at a certain point, the error can come up with a completely different value, which is far away from the ground truth. And this is, in fact, a problem, in particular when talking, and this is what I do very, very often, when talking to metrologists about network-based approaches, then very often the domain experts say, oh, well, but we cannot trust the network. No, the network can produce high errors, and that is a no-go for us. And that's really one of the reasons why in many areas, as I can tell from my experience at least, networks are not so well perceived, because we cannot prescribe an error and be sure that the network cannot go over that error.
Okay, thanks. But it still provides us a clever, convenient, and fast way to see the results in the situations that are not so sensitive to the correction.
Sorry, can you repeat that question?
I said that although there are many accuracy and trustworthy problems, the network-based rendering still provides us a convenient and fast way to see the results.
Right.
Okay.
Yeah. Mm-hmm. Exactly. That's I think what I said at the very beginning. I said if you need a methodology that can efficiently, let me say, give you a fairly good image of the data model, of the volumetric data we have here. Now, then I think network-based approaches are the way to go. If you require 100% accuracy, then networks are probably not what you want to use.
Okay, thank you. Due to the time limitation, we just pick the last problem and last question.
Yes, sure.
Since the nerve, the neural rendering has showed his powerful performance in the graphics applications and in our rendering, volume rendering applications. Do you think there is a possibility to speed up the nerve application methods?
I think so. I mean, what we have done was we have looked at how to speed up nerve on current GPU architectures. I'm pretty sure. I mean, we have to see that the deep learning architectures, not the hardware that is currently used for deep learning. I would say in the future, this hardware will increase or will be, so to say, improved in order to become faster and faster with respect to the specific learning task. So I think this will then also immediately give us performance speed ups for things like nerve. So and this in combination with people, there's a recent paper, by the way, from the NVIDIA guys, where they used nerve-like architectures for global illumination caching. And they also provide very smart and efficient solutions for evaluating these networks. And I think in the near future, we will see significant performance improvements of these kinds of architectures, simply because, first of all, people will think about how to better use existing hardware, and because also I'm convinced that we will get better hardware in order to do these evaluations.
Yeah, so we can looking forward to advances of deep learning architectures and hardwares.
Exactly. And that's the reason why I'm very often in the visualization community, I hear people talking very negatively about network-based approaches, because they say, oh, it's all so slow. And then I say, yes, you're right, I agree. But we need to come up with approaches, or we need to demonstrate that certain things can be done conceptually. And then maybe the performance issue will be solved automatically simply by the next generation of deep learning hardware. No, we cannot just stop here and say, oh, current hardware is too slow, meaning that we stop research. I think we have to proceed with our research and also drive like hardware vendors in order to think about more efficient hardware realizations. No?
Yeah, I totally agree with you. Okay. So our time is up. Let's thank Professor Westermann again for a great talk and great explanations. Thank you all for today's talk.
Yeah, thank you also for the invitation. I enjoyed it. And yeah, if you have questions, just send email and I will be happy to answer. And maybe you have ideas for collaborative work, and then we can join forces in order to drive that process further. I would be happy to do so. Yeah, thank you very much.
Thank you.
Okay, good. Then have a good day, and yeah, hopefully see you soon. Goodbye.
Bye. Bye.